We're going to start by getting a view of the comet because that's what everybody is talking about and photographing. And this is Comet Neowise. I'm sure you've seen photographs of it on Facebook and on the news. And it is just turned into an evening object. And let me get it worked out here. All right, share my screen. There we go. So there's Comet Neowise through the 36th engine. That is the head of the comet, the bright area. You'll notice that it's got kind of a greenish tinge. A lot of people have been, I think we got an echo. I'm going to hit your microphone. Sorry about that. We're still playing with microphones here. All right. Sure. All right. So a lot of people have mentioned that the color has changed to a green tinge in the last week or last few days, and it's very noticeable from here.
Yeah, that's typical of a lot of comets. There is an ice on the comets called cyanogen. And when it sublimates, when it switches from solid ice to a gas, it has that greenish tinge to it. So that's pretty common for comets. So the comet.
You look at this yourself, then you want to be looking underneath the Big Dipper. And it's going to get a little bit higher each night, but right now it's pretty well positioned in the sky. So grab a pair of binoculars if you want, go outside and look just straight down below the Big Dipper, and you might be able to catch it. There we go.
Let's see, is that still a still shot?
Yeah, it's still shot. I'll take the take a fresh one here.
We probably have drifted.
Probably going to have moved.
Yeah, the comet is moving across the sky. It's moving.
Okay, that's pretty good. Yeah, you'll see that in the last 10 minutes of talking, it moved about, an inch across the screen to the left there. So that gives you kind of a sense on the direction and the rate.
Yeah, its motion is actually about 9 arc seconds per minute of time. So we measure distances across the sky using angles, so degrees, minutes, and seconds. 1 arc second is 1/60th of an arc minute, and an arc minute is 1/60th of a degree. So it's moving about 9 arc seconds every minute of time. So it will drift off to the left there, as you noticed. And looks like Richard is playing with his exposures here.
Yeah, I got a little bit more of the tail by stretching the image there a bit. And that's the ion tail. I mean, the
particle tail.
Particle tail. The ion tail would be, if we were able to see it, it would be coming off kind of like this, following my cursor, but I've not been able to get a view of that yet.
Yeah, the ion tail, in all of the pictures that I've seen, the ion tail has been very faint.
Yeah.
If you can just barely make it out in your image, it's going up and slightly to the left, or to the right, rather, in your image, but it's pretty faint. So there are actually 2 tails to a comet, a particle tail and an ion tail or a gas tail. The ices on the comet, there are a number of different kinds of ices. There's water ice, carbon dioxide ice, cyanogen ice, methane ice, and so forth. And as it gets in close to the sun, that ice begins to change from the solid state to the gaseous state. And that's a process called sublimation. And as the ice sublimates, all of the dirt that's in the ice gets released. So there's sand and pebbles and small rocks within the ice, and that is released as the ice sublimates, and the pebbles, the particles we call them, form a long kind of arcing tail that's often white or greenish white in color, and then the gas is blown away from the comet, but it's blown away in a different direction. The gas is blown away from the comet nucleus by the solar wind, and the solar wind is always taking that gas in the opposite direction as the sun is with respect to the comet. The particle tail is always following the path of the comet in its orbit around the sun. So it's not unusual for those two tails to be separated by quite a bit. In fact, in the right configuration, they can actually be going in the opposite direction. So that white bright tail that you see, especially if you take a photograph with your camera, you'll see that bright tail. That's the particle tail. And if you look carefully, you don't see it very well here, but with a wider field of view, you would see that tail has a it fans out and it arcs a little bit rather than being straight back from the comet.
There we go. And so this is M3, and what it is a globular cluster. Now, globular clusters are very interesting agglomerations of stars. There's probably about 150,000 stars in M3, possibly more than that. And they are very old stars. We know that they're old stars by looking at their spectra. The globular clusters orbit in what is called the halo of the Milky Way galaxy. There are about 150 of them in the Milky Way. And another thing we know is that all spiral galaxies have globular clusters. If you have a powerful enough telescope, you could actually see the globular clusters around the Andromeda galaxy and identify them as unique objects separate from stars. And Andromeda probably has a similar number, anywhere from 150 to 250 globular clusters orbiting its galactic halo. And most of the globular clusters in the Milky Way are not this bright. There's about a dozen of them that are notable for being really bright and big like this. Most of them require a dark sky and a good telescope to see. But this one's a particularly beautiful one. And you can notice it has, not just hot blue stars, but it's also got reddish stars in it as well. Do you want to say anything else about globulars, or?
This one is about 33,000 light years away.
Yeah, move on in here.
Yeah. So this globular is about 33,000 light years away. And for many of the globular clusters, there is a suspicion that there is an intermediate mass black hole at the center. And we're not sure about this one, but several of the globular star clusters we suspect have a black hole at the center. The stars are orbiting around the cluster in highly elliptical orbits. So they swing in, get very close to the center. When they're close to the center, they're moving very fast. Then they swing out and they go way out towards the fringe of the globular cluster. And then they're moving very slowly, and then they swing around and they come back in, and they just keep doing that over and over again. By measuring the velocity of the stars and by watching them over time, we can figure out the distance to the globular star cluster, because you see a star move, and you using spectroscopic methods, you figure out its velocity, and then you watch it over time and see how much it moves, what angle it moves, and you can use that to calculate the distance. You can also use the velocity to calculate the mass of globular star clusters. So when we give you numbers like 200,000 stars or 400,000 stars, whatever, that's an estimate based on the calculated mass of the globular star cluster expressed in solar masses. So we assume that the sun's mass is an average star mass, and then we take the calculated mass of the globular star cluster, divide it by the mass of the sun, and that's where we come up with the estimate of the number of stars.
Now, even though this globular star cluster was first observed and recorded in the 1700s by Charles Messier, hence the M in front of the, the designation M3. Whenever you hear us talk about M3, M5, M, 51, it means that it's part of the Charles Messier catalog. Messier was a French astronomer, and he was interested in looking for comets and kept running into these nebulous objects in the sky that were not comets. And so he wouldn't accidentally keep stumbling upon them. He cataloged them. And we have something called the Messier catalog, which is 100+ objects that are reasonably bright. You can see them all from a city location in a small telescope. A lot of people look at them just in binoculars. If you're interested in looking at these objects, just get a hold of a list of the Messier objects and some basic star charts and a decent pair of binoculars and start trying to find them. But these, like I said, this has been known about since the 1700s, but globular clusters have been really poorly understood until recently. Some of the information that Gerald was just giving you has only been, possible to ascertain in the last, couple of decades. Prior to 10, 20 years ago, there were a lot of theories, like one of which was that globular clusters were the cores of old galaxies that had collided with the Milky Way, and all that's left is their core. And, there's still possibility that that may be true for some of these things, but the accepted notion right now is that these massive clouds of gas coalesced into many, many, many stars early on in galaxy formation and created these globular clusters just through the normal star formation process. Now, as far as detecting black holes, the way we can do that is to use X-ray telescopes and to look for either X-rays or for very strong radio sources using radio astronomy. And, that's not always possible to do. It really depends on the distance of the object, the type of object, and, what frequencies you're looking at or listening for. And there are a couple of globular clusters where it's been, most certainly ascertained that there are black holes, but we don't know for sure that all globular clusters have.
Polar ice cap there.
Yeah.
Good.
Yeah, that's pretty good.
Yeah.
All right, so the polar ice cap is at about 7 o'clock, right? That's the more obvious one anyway. And you see that's kind of like a whitish dot that is brighter than everything else around it. That's carbon dioxide ice.
Yeah. So you see some dark features sort of at the lower half of the planet. And the planet is slightly tilted. So the lower third, I guess you'd say, is a little bit darker. That's because that's an older region of Mars. And it's a much more rocky, a lot more craters there. Whereas the lighter region that you see up above, that is a much newer region. It's covered from the volcanoes on Mars, which are all extinct now, but you get a lot, well, you get even better there.
Yep.
Yeah. So the volcanoes are spewing stuff out and it's scattering dust all over the place. And so it's a much sandier region with fewer craters, smoother areas. And a lot of that is actually lower in elevation. So we think at one time Mars had some shallow seas on it. And so if you were to see a image of Mars taken from, say, 3.5 billion years ago, you might see oceans in that part of the planet. But it's all dry now. All the water is either in the ice caps or underground. Right?
This is great.
Yeah,
We
yeah.
have a question. What season is Mars in right now? Well, we can see multiple seasons on Mars because we can see the poles.
Yeah, I'd have to look it up. And Mars is just like Earth, in that one pole has a summer while the other side has a winter.
Yep.
It looks like the southern pole is tilted a little bit more toward us. Am I seeing it that way? In which case,
I'm guessing the side where we see the pole is in summer.
yeah. So that would be the summer side, and the other side.
And I'll tell you, so it's only a, it's like a balmy 70 degrees below zero.
Yeah, right.
It's summer. Yeah, it's not a comfortable place, folks. I mean,
Yeah. Mars is only about half the diameter of the Earth, but like the Earth, it's tilted. Its axis of rotation is tilted relative to the plane of its orbit. So Earth's axis tilt is about 23.5 degrees. Mars's tilt is about 25 degrees. So very similar tilt, but we see evidence that the tilt of Mars has changed over time quite a bit. And the reason Earth's tilt has not changed nearly as much is because Earth has that big moon orbiting around it. And it actually helps to stabilize the tilt of our rotation axis. Whereas Mars, although it has a couple of moons, they're very small. They don't affect the planet very much. And so Mars can tilt more or less than what it is right now.
There's an interesting question from Jasper. Are we sure all of Mars's volcanoes are extinct? How do we know that?
Well, we don't see any activity.
Yeah.
And we do have spacecraft or on the ground at Mars, and we don't detect a lot of volcanic activity. There are some, but not a lot. You may recall a couple of years ago, the InSight spacecraft that landed on Mars. It has a seismometer that has been recording Mars quakes, if you will. And there just isn't much sign that there's any more significant volcanic activity going on there. But we know at one time there was a lot because we still see the old volcanoes. In fact, the highest mountain in the solar system is Olympus Mons on Mars. And to give you an idea how big Olympus Mons is, its height is 3 times the height of Mount Everest. Its base is the size of the state of Arizona. So it's a big mountain.
So if you walked it and climbed up to the peak, it would just be a very gentle slope.
Right. But
it
it's
would just
really
keep going.
It's really high. Okay, so here's the Sea of Tranquility. That's where the first Apollo landing occurred, down in the lower left part of the Sea of Tranquility, roughly where the square is there. You see a bright crater off to the right with some like rays extending out from it. That's the crater Proclus. Proclus is a crater formed by an asteroid that hit the moon at a very shallow angle, causing the ejecta from the crater to spray out in kind of a butterfly pattern. And from that pattern, we can actually tell which direction the asteroid was traveling when it hit the moon. So kind of go farther north here. This is another sea called Serenity. These dark patches are actually lava flows. Very early in the history of the moon, there were some pretty big impacts on the moon, and they produced these big impact basins, but they also cracked the crust of the moon. And back 3.5 million years ago, moved too far there. All right, there we go. Back 3.5 million, 3.8 million years ago, the moon had a molten interior. And so when the crust was cracked by these big impacts, lava oozed up through those cracks and filled those basins. And so those dark areas that you see are actually huge lava flows filling these basins, these old impact craters on the moon. So when you look at the moon with your naked eye and you see dark regions and light regions, those dark regions are the seas, which are actually lava flows on the moon. Right now, Saturn and Jupiter are pretty far apart. If you were to be looking up at the sky right now, Jupiter is a bright object, sort of in the south eastern part of the sky, southeast. And then to the left of it is Saturn, which is not as bright, although it is one of the brighter objects up there. But if you hold your hand at arm's length and put 3 fingers up, the spacing between the 2 planets right now is about the spacing of your 3 fingers held at arm's length. But over time, because Jupiter is orbiting the Earth faster than Saturn, Jupiter is catching up. From our point of view, Jupiter is catching up with Saturn. And in December, they will be so close together in late December that we'll be able to see both of them in the same telescope view. So keep your fingers crossed that the weather cooperates in December, and we might actually be able to see both planets in the same telescope view.
I might point out that they're not close together physically, just angle-wise.
Right. Yeah, John just pointed out it's strictly our viewing angle that makes them look close together. Physically, they are not close together. They're actually quite far apart, nearly 5 million or 500 million miles apart. When they're closest to each other. So you can see Saturn, you see the rings, you might be able to make out a little bit of banding on Saturn's clouds.
I am seeing every once in a while the Cassini division pop in and out right where I'm putting this weird looking cursor. You have to really watch carefully, and I'm just see every once in a while a little black band. And what that is it's a separation in the rings caused by one of Saturn's moons that basically clears a path in all of the dust and ice that forms the ring. I think that's Pan, right? Is that the,
Pan is one of, Pan does the Encke division.
Oh, Pan does the
Cassini.
Encke one. Cassini is a different one. Do you remember which moon does Cassini? Which one causes that?
Actually, Cassini is caused by Mimas, which actually orbits outside of the ring system, but there is a mean motion resonance at the Cassini division with Mimas. So a mean motion resonance, if you have 2 objects orbiting a planet, and it happens to be that the orbital period of one is a whole number multiple of the orbital period of the other. So one, for example, orbits and takes twice as long as the other. We say that's a mean motion resonance, because what will happen is that as one laps the other, it always laps it at the same point relative to the parent planet. So that's called a mean motion resonance. And when you get mean motion resonances, it's very hard for objects at the resonant point to stay put. So what's happening is there's a moon called Mimas, and the mean motion resonance point for Mimas is at about the distance of the Cassini division. So ice particles that get into that part of the ring system want to get kind of shoved back out into other parts of the ring system, which keeps the Cassini division nice and open.
That's very interesting. Thanks.
Yeah.
We had a question. Are Jupiter's and Saturn's core hotter than Earth's core? I mean, honestly, we don't know. We've never sent a probe that far into Jupiter or Saturn. It would take a lot of doing to do so. We don't even really know with any certainty what the temperature of the Earth's core is, right?
Right.
But there's reason to believe that the center of these gas giants have accumulated rocky material that has become molten, and it might be, you know, as hot or hotter than what's at the center of the Earth, simply because there's so much more gravitational force involved, so much more pressure.
Right, right. So the heat, internal heat of a planet can be caused either by compression because of its strong gravitational field and or radioactive decay. Much of the heat in Earth's core is actually the result of radioactive decay. There are radioactive materials down deep in the mantle and the core, and as they decay, they generate heat. And that is what drives much of the heat of the interior of the Earth. So the extent to which that there are decaying radioactive materials in Jupiter's core or Saturn's core, that could contribute to the heat. But you also have a lot of mass, which provides a lot of compression, which also generates heat. So while we're waiting, this is the globular star cluster M15, which is in the constellation Pegasus. M15 is a little over 33,000 light years away.
There we go.
Okay, and so we need to go north a little bit.
Okay, let me abort that. I am going to make it a 20-second exposure at a slightly lower ISO, just so we get a little less noise.
Yeah. So there are about 150 globular clusters orbiting around our galaxy. These are like balls of stars out in space. They're very dense, some more dense than others. M15 is one of the denser ones. In fact, M15 is what we call a core collapse globular star cluster. It hosts somewhere around 400 to 500,000 stars. And these stars orbit around the cluster in highly elliptical orbits. So an elliptical orbit is like an oval. If you can imagine a stretched out oval, many of the stars in the cluster orbit in that highly elliptical orbit. So they go in close to the center and then they swing out. Yeah, I screwed you up there.
That's okay. Don't worry about it. Next one will correct for it.
So they swing way out and then they come back in and they just go round and round and round, going in close. When they're in close to the center, they're moving very rapidly. When they're out far from the center, they're moving very slowly. Now, there are other stars that orbit around the center much closer in, which is why we call it a core collapse cluster. And when we measure the density of the core, it's so dense, there's so much mass packed into that core that there's a strong suspicion that there's actually an intermediate black hole, intermediate mass black hole at the center of the cluster. Now, it's possible that many of the globular star clusters have black holes at their center, but this one has gotten a lot of study because of that very dense core. And when we measure the mass of the cluster, which one way we do that is by measuring the orbital velocities of the stars, and the orbital velocity is a function of the mass of the cluster. So we compute the mass of the cluster and how much of it is concentrated near the center, and it's a pretty good indication that there's a intermediate black hole at the center of the cluster. So this is M15 in Pegasus.
Somebody was asking, what consumer telescope do I need to be able to see something like this? And actually, you don't need a lot. The first time I ever saw M15 was with a very inexpensive 4-inch reflecting telescope. You could also see it through a good pair of binoculars.
Yeah, a 4.5-inch or 6-inch Dobsonian telescope, which is a reflecting telescope, should show this very easily.
Mm-hmm.
This is not the brightest of the globular star clusters, but it's one of the easiest to find. And another even brighter globular star clusters, M13 in the constellation Hercules. And both of these are right at the fringe of being naked eye visible. So if you get in a really good dark location high up in the mountains somewhere, you can actually see them. If you know where to look, you can see them with your naked eye. And
It makes searching for globular clusters a lot of fun, because on one end of the spectrum, there's some that you could almost see naked eye, and on the other end of the spectrum, there are some that are so difficult to find and see that you're never even really sure if you saw them at all.
this big dark area that you see now, this is called the Imbrium Basin. It's one of the largest impact basins on the moon. In fact, I think it is the largest impact basin on the moon. This is an impact that occurred about 3.5 billion years ago. And it was a pretty big impact. In fact, I think if it was much bigger, it would have destroyed the moon. One of the interesting things about it is this impact was so big and so forceful that the shock wave from the impact traveled outward in all directions, sort of like concentric rings of shock waves going around the planet, and they all went around to the other side and converged at a point on the opposite side of the moon, directly opposite from the Imbrium impact basin. And when we were finally able to see what the other side of the moon looked like, sure enough, at that point, that focal point of the shock waves, the terrain is very jumbled and shattered. And that's because all those shock waves came together at once at that one point and disrupted everything. But anyway, you notice the dark, somewhat smooth appearance of the impact basin's floor. And that is because after the impact occurred, that impact cracked the crust of the moon. And then at that time, the moon still had a molten interior. And so over a period of several million years, magma or lava oozed up through those cracks and filled the basin, and created a much newer surface that was smoother. And we see these smooth lava flows on the moon as the dark patches. When we talk about, features on the moon, the man in the moon features, those dark patches are those lava flows. Now up in the top corner, almost in the middle at the very top edge here, I'll try to move the telescope a little farther north. You see a kind of a half circle. That's called Sinus Iridum. And that was another impact that occurred not too long after the Imbrium impact. And it's a crater that sort of overlapped the impact basin crater. And so when the impact basin filled with lava, it also filled that secondary crater or younger crater, and you get that Sinus Iridum, which means sinus means bay. And then to the right, going a little bit farther over here, you see a round crater that's got another smooth floor. That's the crater Plato. And it's also a younger crater, but it filled with the same lava that filled the Imbrium Basin. All right. Coming down south a little bit, now you see a long arcing mountain range to the right. That's actually the rim of the Imbrium impact basin. And we give names to mountain ranges on the moon. We name them after mountain ranges on the Earth. So this mountain range here is called the Apennines. There's one farther up that's called the Alps, and one called the Caucasus. So they're named after mountain ranges on the Earth. One of the Apollo missions actually landed right at the rim. In fact, Richard, if you can put your cursor sort of along there, a little farther down, right about there, there's a channel called Hadley Rill. and that's where Apollo 15 landed. So they were right at the base of the Apennine Mountains, and they collected samples there as well. Now, going a little farther south, and I'm going to center it a little bit more. I got to make sure which direction I'm going here. Whoop, not that direction. So you see a crater with a lot of what looks like splash marks around it. Those splash marks are what we call ejecta rays. And this is the crater Copernicus, and it's a much younger crater, and it was a pretty good size impact from an asteroid. And it threw material out and splashed it all around the crater. You can't see it very well, but there are a number of what we call secondary craters, which was just craters produced by big chunks of rock thrown out of the main crater. And then you see these long, often parallel lines of material that was ejected from that crater at the time of the impact. It's very common for us to see parallel ejecta rays coming out of large craters on the moon. There's some physics involved in why it gets that way. It's a little too complicated to try to explain without using drawings and everything, but it is fairly common. And so that's a relatively young crater. To the left, kind of go.
Speaking of young craters, Little V asks, how often does the moon get new craters, and what is the most recent crater that we can see?
Oh gosh.
That's
Well,
one for you.
It actually gets hit relatively often, maybe once every few dozen years it gets hit by a bigger asteroid. But the moon also gets hit by a lot of small asteroids and what we call meteoroids, very small rocks. You know, the moon doesn't have an atmosphere, and it doesn't have plate tectonics. It doesn't have vegetation. It doesn't have bodies of water or anything like that. So when the moon gets hit by an object, it forms a crater, and that crater stays there. So if we were to zoom way in on one of these craters, we would see that there are more craters on top of craters on top of craters. And because it doesn't have an atmosphere, even a small rock, the size of a basketball or even the size of your fist, can make it all the way down to the surface and punch a hole in the surface and make a small crater. Now, the same thing happens to the Earth. In fact, the Earth gets hit 16 times more often than the moon does. But small asteroids or rocks out in space burn up in our atmosphere. And we see those as shooting stars or occasionally fireballs and things like that. Those objects, you know, are maybe the size of a basketball or maybe the size of a small desk or something. They enter our atmosphere here on Earth and they burn up. But on the moon, those objects would continue all the way down to the surface and produce a crater. So in reality, the moon is getting hit frequently. I would say several times a week, probably, but mostly by very small objects. Occasionally, it gets hit by bigger objects that produce craters that are easily seen from the Earth, but that's actually pretty rare. Maybe once every few years, it'll get hit by something that produces a fresh crater that we can see easily with a telescope from the Earth. When was the last one? I can't tell you, but I know every once in a while I'll see some write-up about a new crater that has appeared on the moon. Another crater with a pretty distinctive splash pattern or ejecta pattern around it to the left of Copernicus is the crater Kepler, which is a smaller crater than Copernicus, but it also has some pretty distinctive ejecta patterns. So we're doing a 30-second exposure of M57, the Ring Nebula. The Ring Nebula is what we call a planetary nebula. It's gas shed by a dying star. So this star was once probably very similar to our sun. but it got very old. As it got old, it swelled up and became a red giant star. As a red giant, it began losing its, now there it is. All right.
Well, that's much better than I expected.
Yeah, that's
So that's excellent. The star that created this this ring of gas has evolved into a white dwarf star, and you can see it in the center of the ring. And if I point it out, in fact, right, find my mouse now, right there. You always know where it is by looking for the arrow. There it is. So you could see the white dwarf star in the center of the planetary nebula. And all planetary nebula will have something like that. Whether you could see it or not depends on whether or not you're looking into the poles of the planetary nebula, or if you're looking at it from the side. And in this case, the pole opens up right towards us.
Yeah, so I was explaining a little bit about what planetary nebula are. The star, as it gets old, it becomes a red giant. And as a red giant, it is very large, can be more than 100 times its original size. So imagine this is what's going to happen to our sun here in about 6 billion years. Imagine the sun being more than 100 times its current size. When the star is that big, its gravitational hold on its outer layers is pretty weak. At the same time, there's a lot going on within the star. There's a lot of turbulence and convection going on, which produces strong winds. And those winds can literally blow the outer layers of gas off the star out into space. And see Richard's playing around with stretching the image here a little bit. So the star begins to lose its mass. Over 100,000 years or so, it blows gas out into space, losing its outer layers, eventually exposing the inner layers of the star, which are much hotter. And at some point, the star also runs out of fuel at its core. When it runs out of fuel, the fusion process, which has been producing all the heat of the star and which produces the internal pressure, which keeps the star expanded, that fusion process stops, and what's left of the star collapses into what's called a white dwarf. Now, this is a star that maybe was 1 million miles across when it was nice and young and in its vigorous years. As a white dwarf, it has shrunk down to be maybe 8,000 or 10,000 miles across. So it's much smaller, but it still has all of the heat that it had just before it collapsed. And that heat is now condensed into a very small space. So the star becomes extremely hot. And the star is also composed of a different kind of matter than ordinary matter. It's what we call degenerate matter. And with degenerate matter, it has to do with the structure of atoms and the electrons and their ability to absorb energy. As a result, the star is emitting a lot of heat, but there's no fusion or anything like that going on. It's just emitting all that residual heat that was left over from before it collapsed. And that heat, because it's so intense, comes off to a great extent as ultraviolet radiation. And the white dwarf is surrounded by all the gas that it was expelling before it collapsed. And the ultraviolet radiation goes out and it hits that gas, ionizes it, and causes it to glow. And the colors of the gas that we see is dependent on the composition of the gas. So if you look at Richard's image here, you see at the very outer edge, it's red in color. And that means that there's a lot of hydrogen there. In fact, the cloud is mostly hydrogen throughout. But at that very edge, there's a lot more hydrogen. Hydrogen, when it's ionized, glows in a deep red color. We call it hydrogen alpha. And so that red color that you see tells us that there's hydrogen there. But there's also in this cloud a small amount of oxygen. And oxygen, when it's ionized, glows in kind of a bluish green color. So you see a lot of blue-green in the cloud. Now, based on the coloring, you would think, okay, that means there's a lot more oxygen than there is hydrogen. But that's actually not the case. The oxygen is quite a bit less than the hydrogen, but oxygen, when it's ionized like this, it glows really bright in that blue-green color, whereas the hydrogen glows a very dull red color. So the oxygen, even though it's the quantity-wise, there's less of it there, brightness-wise, it overwhelms the red color of the hydrogen.
I'd also like to point out one other factor. We're using a DSLR camera, which is this is a standard off-the-shelf Canon camera that you can get at Costco, right? So the camera itself is much more sensitive to green and blue than it is, or green in particular, than it is to red. For every red pixel, there are 2 green pixels. And so as a result, it is biased towards the oxygen part of the spectrum. And to make matters worse, these cameras have an infrared filter over the sensor that blocks out probably, I don't know, 30% or so of the red color that you would normally get from an object like this. And there are actually places you can send your camera to have surgery done on it to remove that red filter for astrophotography purposes. But that's aside from the fact that the oxygen does glow much more brightly than the hydrogen when it's ionized, the camera is also biased towards the part of the spectrum that the oxygen glows in.
Okay, so this is a planetary nebula. This is the Ring Nebula, but the class of nebula that you see is called a planetary nebula, and there are actually a lot of them out there. There are many stars that go through this process. The cloud that's shed by the star can be very symmetrical. This one looks like a ring. We're pretty sure, though, that what you're actually looking at is down the tube of a cloud of gas that looks more like an hourglass. So it's very common when these stars shed this gas, it comes off the poles in sort of an hourglass pattern. So if we could somehow take that cloud and turn it 90 degrees, it would have an hourglass shape to it. It just happens to be oriented, so we're looking right down the tube, giving it that ring appearance. So we're looking at the northern part of the moon. That big round crater with the smooth floor, that's called Plato. And Plato is an impact that actually occurred after most of these larger impacts occurred. But it did fill with lava the same way as the large sea that you see to the south. And we'll talk about that sea in a minute here. If you look just north of Plato, you see a large smooth area that's called Mare Frigoris. Mare means sea, and so that's the Sea of Frigoris. I forget what Frigoris means, but that's Mare Frigoris. If you look down and to the right, you'll see a couple of craters. Rich, you may have to do the pointing here. So.
Yep.
Down and to the right, there's 2 craters. Right up.
Oops. Right there.
Yeah, I can't see your cursor.
Yeah, unfortunately, the cursor does not.
Yeah. All right. Okay. So you see 2 craters. The upper one is a little bit bigger than the lower one. Those 2 craters are Aristoteles and Eudoxus. And then between those 2 craters and Plato, you see kind of a range of mountains. That range is called the Alps. And if you look very carefully, you'll see a kind of a straight trench or valley or something like that right across there. that is a graben. It's an area where the mountains have slumped down in a crack. And the reason for that is that large smooth area to the left is called Mare Imbrium. Mare Imbrium is the largest impact basin on the moon. It's very large. I'll move it down here a little bit so you can get an idea what I'm talking about. So this large smooth area that you see below Plato is the impact basin called Mare Imbrium.
It's okay.
And it has filled with lava, so it has that dark coloring. And you notice there are very few craters there, which tells us that lava flow is a lot younger than the moon is. The moon is somewhere around 4.5 million or billion years old, 4.5 billion years old. And there's some debate about the exact age. There's a recent paper that came out that suggests it's a little bit younger, like about 100 million years younger than what we previously thought. You know, that's typical in astronomy. As we get more data, we adjust our thinking about a lot of things. So looks now like maybe instead of being 4.5 billion years old, it might be 4.4 billion years old. When it first formed, it formed because of an impact with the Earth. There was an object floating around, a small planet about the size of Mars, that impacted the Earth. And that impact threw material out into space, which then initially formed a torus, like a donut around the Earth of rocks and material that eventually coalesced to form what we see now as the moon. And initially the moon was much closer to the Earth. Over the centuries and eons, it has moved away, and it continues to move away. The moon is moving away from us about 1 inch per year. And that's because of an gravitational interaction with the tides on the Earth. So anyway, the impact that produced the Imbrium Basin happened very early in the moon's history. You then had over several million years this lava flowing up and filling the basin, and then you had other craters formed later on. But early in the solar system's history, there was a lot of asteroids and comets flying around, and many of the craters, in fact, most of the craters that you see on the moon are extremely old, on the order of several billion years old. The moon has no atmosphere, has no waters or streams or anything like that to erode the surface. There's no plant life or animal life. So there's no weather. So you punch a hole in the moon, that hole stays there for billions of years. Some of you may have seen the footprints left on the moon by the astronauts. Those footprints will still be there 1 million years from now. So things kind of stay pretty much the way they are for a long time on the moon.
Hey, Charles. There we are. Jupiter and Saturn.
All right. So Jupiter and Saturn in the same field of view of our telescope. We're actually zoomed in a little bit here. So if we were to back out a little, I think we could see even more. Yeah, there you go. So this is Jupiter and Saturn. They're both in the same part of the sky. They're so close to each other that if you're looking at it with your naked eye, you might confuse them and think that they're one star that's somehow elongated or distorted. But in fact, they are just in the same line of sight. The distance between them is actually about 455 million miles. So they're, out in space, they're not very close to each other at all. But because of the alignment of the two planets and their orbits, we see them both in the same field of view tonight. And this is an unusual event. The two planets pass each other about once every 20 years. Most of the time, they're still fairly far apart in the sky, but once in a while, they get really close together. We had one about 800 years ago. We had one in the year 1166, another one in the year 1226, and a very close one in the year 1623. So this happens every once in a while, that we get these really close conjunctions, and they're really exciting to see.